Okay, welcome to chapter 14, which is about direct current. When we mention the word current, we know that there are some moving charges. And then in our cases now, the moving charges are now free electrons. So what are the free electrons? Okay, this is a picture of an atom. Inside the atom, we have a massive nucleus which is made up of protons and neutrons. And then outside the nucleus, we have some orbiting electrons. Those orbiting electrons are bound electrons because they are bound to a certain nucleus. And then the electron in the outermost shell is most loosely bound ones. Okay? That means that the electrons in the outermost shell are most loosely bound. That means that if you are able to give them some energy, for example, some thermal energy by raising the temperature of the conductor, or maybe you can provide some electrical potential energy, then those bound electrons can get very energetic, and then finally they are able to move in the space between the atoms of that material. That means that the bound electrons are now no longer bound. So we call them as free electrons because they are free to move everywhere. For example, this is a circuit. If the electrons are able to move here, here, then you say that the electrons are free electrons. However, if the electrons are stuck somewhere, that means that if the electrons may be stuck here, or maybe the electrons are stuck here, it means that they cannot move anymore. They can only orbit around a certain atom. Then we call them bound electrons, and they are not free electrons. Okay, and then normally conductor has a lot of free electrons, and then semiconductor has very little free electrons, and then the insulator almost has no free electrons at all. We will show this later, okay, which is here. We will show this later, okay. First of all, we need to explain the mechanism of electrical conduction in a conductor when it is connected to a battery. Okay, in the conductor, normally the free electrons are the charge carriers. And then let's say, now without an electric field, you know that the free electrons move randomly with a high speed of about 10 to the power of 5 or 6 meters per second. And then the free electrons now can move due to the thermal energy. Okay, the net velocity of any free electrons over a certain period is zero. No net flow of charge and therefore no electric current. Okay, however, when the conductor is connected to a battery, then an electric field is set up, and then a potential difference V is applied across the conductor of length L. Okay, you know that electric field equal to the potential difference over the length of the conductor. The electric force F is produced, and then free electrons drift from region of low electric potential to region of high electric potential. Okay, F equal to QE, which is from the definition of the electric field strength. F equal to ma, which is from the Newton's second law. Okay, and then you have to label, that means that Q is the charge of an electron, which is 1.6 times 10 power negative 19 coulomb. M is the mass of an electron, which is 9.11 times 10 power negative 31 kilogram. And then A is the acceleration of the free electron. When the electrons are accelerated by the electric field, they will collide with the lattice atoms or ions. And then the electrons will have a net velocity called drift velocity. And then the magnitude of drift velocity is 0.1 millimeter per second. You realize that the magnitude of the drift velocity is much smaller than the magnitude of the random high speed. Okay? So first of all, we need to prove the free electron density equal to this formula. Okay, just now I already introduced you to what are free electrons. Now, if I want to say how many free electrons per unit volume, then this is the free electron density. Okay, so first of all, number of moles per unit volume is like this, and then 1 mole is equal to the mass divided by the molar mass, where the molar mass is the mass of 1 mole of the substances. Okay, and then the V and the M is changed places. Mass divided by volume is the density rho. Then the molar mass is here. So now free electron density is the number of free electrons per unit volume, which is equal to number of moles per unit volume times the number of atoms or molecules per 1 mole. And then the number of atoms or molecules per 1 mole is the Avogadro's number, which is 6.02 times 10 power 23. And then just now you know that mole per volume is rho per m. Okay, so this is the result. Okay, remember that the rho here is the density of the material. Okay, because later on you will also realize that the resistivity is also denoted as rho. Okay, but then when the symbol clashes, then you have to give your different symbols to denote them, so that the symbols do not clash. Okay, so now we want to derive I equal to nAve. Okay, so this is a conductor, and then the current flows through the conductor, and then the conductor has a length L. Okay, so charge of 1 free electron is like this. The volume of the conductor is equal to the area times length of the conductor. The cross-sectional area of the conductor is A, and then you remember that the cross-sectional area refers to the area that the current flows through. The length of a conductor is L. Okay, total amount of free charges inside the conductor Q equal to total number of free electrons inside the conductor times E, which is Ne, and then N is equal to small n times volume. Small n is the free electron density, which is the one that I derived just now. Okay, this is the free electron density. This is the free electron density. Okay, then the volume equal to area times the length of the conductor. And then the current is defined as the rate of change of the charge. So you know that you are going to differentiate this with respect to time. Normally in school, you straight away jump from this step to this step. Okay, but then I need to tell you that during this process, you are actually doing the partial derivatives. That means that you differentiate this and then keeping these 3 terms constant. You differentiate this and then keeping this and this constant. You differentiate this and then you keep these 3 constant. You differentiate this and then you keep these 3 constant. Okay? Normally for a certain conductor, the number of free electrons per unit volume, which is n, is a constant, and therefore dn equal to 0. And then for conductor of constant area, then dA is also equal to 0. dL over dt is equal to V, and then V is the drift velocity of free electrons. Okay, and then dE over dt is equal to 0, because you know that the charge of an electron is just a constant value, which is 1.6 times 10 power negative 19. So when you are differentiating a constant, you know that you are going to get 0. So you know that these 3 terms have 0 value, and then you only left with this term. Okay, if you are asked to give the definition of the drift velocity, then this whole thing would be your answer. Drift velocity of free electrons is the average velocity of free electrons in a conductor when an electric field is applied around the conductor. When free electrons are accelerated by electric field to move from low electric potential to high electric potential, they will collide with the lattice atoms of ions, and then the net velocity of free electrons is called drift velocity. Okay? Just now you already learned that the magnitude of the drift velocity is very small compared to the high speed of the random electrons, which is this one. You know that the magnitude of drift velocity is like this, and then the magnitude of the random high speed of electrons is like this. Okay, this is much bigger than this. Okay, and then the drift velocity is what you are getting just now. And then current density is equal to current divided by area, and then area is the area where the current flows to. Okay, so I equal to nAve divided by A. The A cancels out. You only left with nVe. So you know that the expression for J is nVe. Okay, for example, you are now given a rectangular conductor like this, and then the current flows from here to here. You know that inside the nAve you need an area, and then the area is A1, A2 or A3. The answer is the area is the A1, because A1 is the area that the current flows through. Okay, just now you already get the current density equal to nVe. Okay, and then inside a conductor, we know that the electric field will exert an electric force on the free electrons. So F equal to EE, which is from the definition of the electric field strength. And then F equal to MA, which is also equal to MV over tau. F equal to MA comes from the Newton's second law. Okay, and then acceleration equal to drift velocity divided by tau. Okay, tau is the average time intervals between successive collisions, or mean free time of free electrons. Okay, so now you imagine this is your free electron, and then these three are the other atoms of, or the other electrons. And then when your free electron is being accelerated, it will collide with this, and then collide with this, and then collide with this. Okay, so this is the first collision, this is the second collision, this is the third collision. The time interval between the first collision and the second collision is the first free time. And then the time taken between this collision and this collision is the second free time. Okay, and then you are doing the averaging of all the free times, then only you get the mean free time. Okay, remember I used the word time intervals between successive collision. That means that between this and this collision, not between this and this collisions here, because it collides with this, then only this, then only this. Okay, and then if you use the time of collision, that means that the time of contact between this free electron and this atom. So be careful of the usage of the word. Please use the word between, not the word of, because if you use the word of, time of collision means the time of this free electron in contact with the atom. Okay, so you use the word between, not the word of. In order for you to understand the mean free time of free electrons, I want you to imagine this is a free electron, and then these are all the other electrons or the other atoms. And then when the free electron is being accelerated, it will surely collide with the other atoms or electrons. For example, it will be like this. Okay, so this is the first mean time, this is the second mean time, this is the third mean time, this is the fourth mean time, and this is the fifth mean time. And then the average of them is your average or mean free time. For example, if this is 5 seconds, this is 5 seconds, this is 10 seconds, this is 5 seconds, this is 5 seconds, then your mean free time would be 5 plus 5 plus 10 plus 5 plus 5 and all divided by 5, which is equal to 6 seconds. So your mean free time would be 6 seconds. Okay, so coming back to here, F equal to ma equal to ee, and then you can get the expression for the drift velocity, and then you substitute the expression for the drift velocity into this, then you can get J equal to sigma E, where the sigma is equal to conductivity of the conductor. Okay, the conductivity of the conductor is the reciprocal of the resistivity. That means that 1 over conductivity equal to resistivity. Okay, and then by the same reasoning, 1 over resistance is equal to conductance. That means that the resistance is the reciprocal of the conductance. And then the unit for conductivity is Siemens per meter, or you can say that per ohm per meter. And then the unit for the resistivity is ohm meter. Normally we say that conductivity is equal to 1 over rho. So normally we use this unit instead of this unit. Okay, so normally we use per ohm per meter as the unit for conductivity. So now you know that conductivity equal to Ne squared tau over m. E is just a constant, which is 1.6 times 10 power negative 19. M is also a constant, which is 9.11 times 10 power negative 31 kilogram. So you know that conductivity is directly proportional to N and also tau. If tau increases, then the free electrons have longer time to drift, which is in between collisions, so that the free electrons can drift further away inside the conductor, and therefore the conductivity increases. Okay, so what happens if the mean free time tau increases? That is, the distance between your collisions increases. Okay, so that the mean free time of this free electron actually increases. That is, the free time here increases, the free time here also increases, the free time here also increases, the free time here also increases, and then the free time here also increases, so that your free electron can drift further away inside the conductor. If N increases, then conductivity also increases, because now you have more charge carriers inside the conductors. Okay, what is Ohm's law? Ohm's law states that electric current flowing through a conductor is directly proportional to the potential difference across that conductor, provided the temperature of the conductor is the same. Okay, so you know that V is directly proportional to I, and then normally when it's a directly proportional relationship, we use a constant which is K, and then we realize that this constant is the resistance. Okay, so V equal to IR is the Ohm's law. Okay, now you know that the resistance of conductor is directly proportional to the length of conductor, and then the resistance of the conductor is inversely proportional to the area of the conductor. So by using this relationship, you get this relationship. And then when it's a directly proportional relationship, you put a constant here. Okay, and then the constant is the resistivity of the conductor, and then 1 over resistivity is equal to conductivity. Remember that the conductivity or the resistivity depends only on the types of material and temperature. That means rho does not depend on L and also A. Okay, rho only depends on the types of material and temperature, because it's a property of the material itself. And then please show that J equal to sigma E and Ohm's law, which is V equal to IR, are equivalent. Okay, J equal to I over A, and then you know that V equal to IR. Okay, then you change I into V over R, and then you know that R equal to rho L over A. Okay, and then the A can cancel out each other, and then you know that V over L is equal to electric field, and then 1 over resistivity equal to conductivity. So finally you can get J equal to sigma E. Okay, Okay, so these are the band diagrams for an insulator, a semiconductor, or a conductor. The y-axis is the energy of the electrons, and then the purple color denotes the conduction band. That means the electrons in this band are free electrons. Okay, you remember what are free electrons here, because just now I introduced you what are the free electrons. Okay, free electrons are the electrons that are able to move in the space between the atoms of that material. Okay, so you know that the electron in the conduction band is a free electron. Okay, and then the red color represents the valence band. That is the outermost electron orbital of an atom. Okay, you remember the valence band means the electrons in the outermost shell. Okay, and then the spaces in between the conduction band and the valence band is the band gap. Okay, you realize that for an insulator the band gap is very large, and then for a semiconductor the band gap is quite small, and then for a conductor you do not have a band gap. That means the conduction band actually overlaps with the valence band. Okay, and then this is very important because you know that for an insulator the electron needs to get a very large amount of energy so that the electron can be promoted into the conduction band. When the electron is in the conduction band, then only the free electron can help you to conduct electricity. That means if the electron is inside the valence band, they cannot help you to conduct the electricity because they are still bound to a certain atom. They are not free electron. Okay, and then for a semiconductor the band gap is smaller, so the electron only needs a very small amount of energy so that they can be promoted to the conduction band, so that they can help the semiconductor to conduct electricity. And then normally the energy that can be given to the electron is in the form of thermal energy or electric potential energy. Okay, if you want to give the energy to the free electron, you need to increase the temperature. If you want to give electrical potential energy to the electron so that it can be promoted to a free electron, then you have to use some power source, maybe a battery or some other power sources. And then for the conductor, actually since the bands are overlapping, therefore the electron, they do not need any more energy to be promoted into the conduction band because they are already inside the conduction band. Okay, please explain how the electric conductivity of a conductor depends on the change of temperature. When the temperature increases, the lattice atoms vibrate with greater amplitude. The free electrons will collide more often with the atoms. This reduces the mean free time between the collisions and decreases the drift velocity of electrons. So the conductivity of the conductor decreases when temperature increases. Okay, when conductivity decreases, then the resistivity increases because you know that the resistivity is the reciprocal of the conductivity. Okay, so when temperature increases, the mean free time of the electron decreases, and then when the mean free time of the electrons, the mean free time of the free electrons decreases, then the conductivity decreases. Explain how the electric conductivity of a semiconductor depends on the change of temperature. When the temperature increases, more electrons will jump from the valence band to the conduction band to become free electrons. That means the electrons in this band will be promoted to this band when the electrons are gaining some extra energy from the thermal energy when the temperature rises. Okay, so the number of free electrons in semiconductor increases, and therefore the conductivity of semiconductor increases. In fact, when temperature increases, you know that actually there is also additional vibration of atoms inside the semiconductor. That means the mean free time still decreases when the temperature increases. However, for the semiconductor, N will increase when the temperature increases. Just now for the conductor, N is just a constant because all the electrons are already inside the conduction band. They do not need to be promoted anymore. So for the semiconductor, you know that the electrons can be promoted from the valence band to the conduction band, and therefore N will increase, and then the effect of this is much more dominant than this. That means that this increases has a greater effect than tau decreases. So when N increases, you know that sigma, which is the conductivity, increases. And that's why we say that when temperature increases, the conductivity of semiconductor increases. And then just now for the conductor, when temperature increases, the conductivity decreases.